everyone, welcome to Diksha Vedantu, where we teach science with fun and proper imagination. I'm your Aditi Ma'am, and in this today's lecture, we are going to see a very important chapter, that is human eye and the colorful world. We'll do theory as well as lots of questions and numericals. Almost all of the students undermine this chapter thinking it's easy, it's okay to just skip it and skim through it, but the numericals can be really hard once you go into it, and these numericals will directly come into your examination and can cost you 2 to 3 marks. So make sure you watch this video till the end. This lecture is very interesting. We study about the human eye. So ma'am, it should be biology, right? But we study about the image formation in the eye, the defects in the eye lens, and that all comes under the physics section of our science. Okay. So beta, before starting this chapter, make sure you are giving it the importance it deserves, because then only it will give you the marks you deserve. Okay. Now, the first thing in this chapter we are going to see about is actually the outline of the chapter. But before that, have you seen these beautiful eyes? You have all seen the animes, you have seen the Ghibli trends, right? And we have different colors of eyes. We have seen some green, brown, black, blue, right? So I have a question for you, and before you start this video, let me know if you know the answer. Which color of the eye do you like? Which color of the eye you have? Or do you know which part of our human eye actually gives us the color? Actually gives the color to our eyes. Okay. Now beta, in this chapter we are going to start with the very basic, that is human eye and its parts. Now in this particular section, the diagram is very important. Okay, the diagram of human eye is very important. They used to ask it almost every single time in boards, but recently it's a little bit here and there. Sometimes they ask, sometimes they don't, but we are going to prepare for the 100% marks. Okay. Parts is where the questions or the MCQs will come from. Okay, so again, a very important thing here. Then power of accommodation, defects of vision and their correction. We know 3 kinds of defects, right? So we'll study about that. Dispersion of white light by a glass prism. Now this is a complete different section. This is your first section, and this will be the second section of this particular series. Now beta, in this particular video, we are going to do lots of questions, all the MCQs, assertion reason questions, numericals, theory questions, diagram questions. So make sure you watch the video till the end, and if you watch the video all long, you won't need any single thing for your boards, let alone PT test, half yearly. For even boards, you won't have to worry about literally anything. Okay, great. Now starting with the very first bit, this is how your human eye looks like. We have so many parts. We are going to study about functions of all of these parts in a very careful manner, in a very lovely manner. Okay, now starting with the very first beta, take out your spectacles and open your eye. Okay, and try to touch inside your eye. Try to touch it. Don't hurt yourself. But the thing you touch, the first thing that touches your finger when you touch your eye is your cornea. Okay, it is your cornea, the liquidy substance, a little bit of watery liquidy substance, that's your cornea. Now what is it? Beta, it's a dome shaped structure. So obviously you know eye is a little round shaped, right? So it's a dome shaped structure in front of your eye, in front of your lens, it's the first layer. So it's a dome shaped layer on the front surface of the eyeball. That's the main definition of cornea. What's its function? Now you know we all have a lens, right? But that's not from where the light refracts. We have studied in light chapter, right? Lens refracts. We have a lens in our eye. So refraction happens inside the lens. But in our eye, most of the refraction happens due to cornea. Now cornea has a different medium, right? There is air, and when the light enters, it touches the cornea first. So it's going to refract because there's a change in medium, right? So that change in medium where the light refracts or bends the most for the image formation is the first part, that is cornea. So it refracts or bends most of the light entering into the eye, helping to focus it on the screen. let's say there is a screen in our eye at this moment. Let's understand it like this. There's a screen, so this cornea, the light is coming, this is cornea, okay? So it refracts the rays. Done. Now, if this cornea is missing, if you don't have a cornea, then your eye won't be able to refract the light, focus it on the screen, right? If the light is not focused on the screen, how the image will be formed? So image will be very blurry, and it is the first focusing surface, so image will be very blurry or no image will be formed. That's how important this cornea is. Okay, so that's the first part. Which part? See, this is the dome shaped, the outward bulged on the eye, the outward bulge on the eye. This part is called cornea. Okay, understood? Great. Moving on to the next part. After this cornea, beta, we have iris. Now, answering the question that I asked first, which part of the eye gave us the color of the eye? That is your iris. Now, what does iris do? The colored part of the eye, okay, in the center we have a round shape from which technically we see, right? That part has different color. Mine has brown, someone has black, someone has green, blue or orange, nobody has. But that colored part of the eye, that color to the eye is given by iris, okay? It is given by iris. Now, this is not the only function of iris, just giving the color. It's not that just to give the color. The function is it controls the size of the pupil. What is pupil? Now, you have to take it side by side. If you understand iris, you understand pupil, you understand pupil, you understand iris. Now, pupil is what, beta? It's like the camera. So you see, when you click a photo, technically you've seen big cameras, it shutters like this. Pachak, right? So that is pupil. It is a shutter of the eye. What it does is, see, whenever you have heard it about it, right? Or you have experienced it, whenever you enter into a theater and it's all dark, pitch dark, and you won't be able to see anything, right? But there is small light, but still you won't be able to see much things. Then you give yourself a little bit time, 30 seconds, 40 seconds, and now everything is visible. Okay? Why does that happen? Why does that happen? That happens because pupil is adjusting itself. Why? Pupil is in the sun, okay? And you see, when you go from a theater directly into the sun, a warm light sun, you see you'll have so much pain, you'll close your eyes, too much light, right? What happens? There is pupil, right? So we don't want so much light to enter into our eye, right? So pupil closes when we are in sunlight, when we are in too much light. So it closes, not closes, it closes a little bit. Okay, if it closes, no light will enter. So it's technically the door for the light inside our eye. So it gets smaller. Now less light is going on, less intensity of light is going on. So you'll be able to see properly. But when you enter into the theater, now pupil is still this small. So a lot of light, you can't see anything because there is no light. So less light, no light, plus there is less light going into your eye. How will you able to see? Right? So pupil slowly expands. It says, okay, less light is there. Let me expand. So it expands and now it's bigger and it's capturing all the light that it can so that you are able to see the stuff, right? So that is the function of pupil. Now, pupil is controlled by what? It is controlled by iris. Iris shuts the pupil down when we are in sunlight. Iris opens the pupil up when we are in a theater, in a dark room. Okay, it controls the size of the pupil like a camera shutter to adjust the light entering inside our eye. Okay, now if it is missing, too much or too little light would enter. Okay, your pupil will not close, so a lot of sunlight will enter, or your pupil will not open, so no light will enter when you are inside the theater. Vision would be painful, right, and completely dark in the bright light. Okay, do you know, we have a do you know section. Everyone's iris pattern is unique. It is for the biometric security scans. So just as we have different thumbprints for every person, fingerprints for every person that exists on this planet, every person have a different eye print as well. That is because of iris blueprint. That's why you've seen face recognition. So basically they recognize your eyes, not your face. Okay, face are also there, but normally they recognize the pattern of your eyes, and for everybody eyes the pattern is different, right? So that's the main thing for face recognition or biometric security scans we use for, right? Next beta, pupil allows light to pass into the eye. That's the main function of pupil. Now if it is missing, no light will enter, we wouldn't be able to see at all. Okay, so in dim light your pupil gets bigger. As we said, we enter into the light at dark area, your pupil will get bigger. We enter into the sunlight area, we enter into the light lit area, your pupil will get smaller to adjust to the intensity of light that is entering inside your eye. Done? Great. Next beta, next part, then you see aqueous humor. Okay, I forgot to tell you on where this iris and pupil are. Okay, so this is the cornea, right? This is the cornea part, correct? The outer bulge. Next beta, we have iris. Just after this part, can you see this red part? This red part, this is iris. This is iris. Okay, after that pupil, this part in between the red part, see, even if you see your eye, you will see there is an outer circle, there is an inner smaller circle. That smaller circle is the pupil. The outer circle which has the color, it is iris. Done? Next beta, we have aqueous humor. Now talking about aqueous humor, what is aqueous humor? It is a liquid watery fluid, okay, between what? Between your cornea, the front layer, and the lens. Now you obviously have a lens in our eye, so it is a fluid between the outer part and where the lens is kept. Okay, so that's the basic aqueous humor. What is its function? It maintains the shape of the eye and nourishes cornea lens. Nourishes cornea and lens. So see beta, everything in our body needs blood, needs oxygen, right? Everything in our body needs oxygen, but this cornea, it does not get oxygen in from our blood vessels. Our body gets oxygen from blood vessels, right? But cornea does not. Cornea gets oxygen from the air. It breathes, yes, it gets oxygen from the air, and when it gets oxygen, it gets dust particles as well, right? But it gets some nutrients, some other gases as well. So the main part of this fluid is to see, cornea is getting nourishment from the oxygen. So main part of this fluid is to give the nourishment to cornea as well as lens as well. Okay, someone has to nourish the lens as well, right? That's what this aqueous humor does. Okay, now if it is missing, eye would literally collapse and lose its proper shape, that is blood vision. Okay, vision will be blood. In dim light, your pupil, okay, this is the wrong, do you know, we have incorporated here. Okay, moving on. Now this is beta, this is the fluid between cornea, this was the cornea, and this is your lens. This is whole part is your lens. So this fluid inside the cornea and the lens will be your aqueous humor. Done? Moving on, after aqueous humor we have lens. Now we talked about lens. Which lens is it? Do you guys know which lens is it? Comment down in the comment section if you know which lens is this. This lens beta is our convex lens. We studied about convex lens, right? So this is your convex lens. Done? Now beta, talking about this lens is the most important part of your eye. Everything is important, but this is also important. So this is transparent, and a very important property, this is flexible. What do I mean by flexibility? I'll tell you in a second. Now pay attention. What is it? Transparent. It is flexible, convex lens behind the pupil. This was pupil, right? This was pupil. So this thicker part is your convex lens. Done? What is its area? What is its function? Ma'am, light is coming. It focuses it on the retina. It focuses it on the retina. Retina is what? Retina is a screen where the image is formed, right? So it focuses every light on a screen so that we can see the image formed. Done? If it is missing, no focusing, no image form will be blur, because cornea refracts the light, but it can only refract some amount. The other will be refracted by lens now. So 2 times refraction is happening inside our eye, right? So similar to a camera without a lens. Okay, there will be camera, but there will be no lens in the camera. So what will capture the light? Nothing will capture the light. What will focus the light? Nothing will focus the light. So blurry image will be there, or no image will be there. Okay, now the pain point, the lens changes 20,000 plus times a day as we look near and far. A very interesting point. Does this come after that? Yes. Okay, let's study about this very interesting point. That is, beta, now we said that this lens is flexible. What do I mean by that? See, this is your convex lens. Okay, this is your convex lens. So it gets smaller, it gets larger, it gets smaller, it gets larger. When we have to see near, it gets smaller. When we have to see farther, it gets larger. So as we can see far things clearly as well, and the nearby things clearly as well. Okay, that is, this whole thing, beta, is called power of accommodation. What is power of accommodation? So the power of accommodation is the ability of my eye lens, how much it can contract, how much it can relax, and while it contracts, this is the lens contracted, this is the lens relaxed. So both of their focal length will be different, right? Both of their focal length will be different. So the ability of the eye lens to change its focal length so that we can see nearby and distant objects very clearly is the main objective why our lens is flexible. Done? How this works, we'll come back to it after reading all other parts of our eye. Okay, so this was crystalline lens, this is a convex lens. Understood? So what did we study till now, ma'am? This is cornea. This is my aqueous humor which provides nourishment to cornea and lens. Then beta, we have this one is, ma'am, pupil. Ma'am, this one is iris. This pupil is the shutter. It closes, it opens. Iris helps pupil to close down or open up. And then we have this crystalline lens which is convex. A very important property is it is flexible. Done? Learn it with me. That's the main objective of this whole video. You have to learn it with me. After you end this video, you don't have to open the book again. That's my objective. Okay, great. Now next thing is beta, vitreous humor. Ma'am, aqueous humor, vitreous humor, yes, one and same thing but at a different position. So aqueous humor was between cornea and lens. Now this is between eye lens and your retina. This is between your eye lens, this eye lens and this retina. So what is this whole thing is filled up with? This is filled up with a fluid that is called vitreous humor. What it does? It maintains the eye shape. It maintains the shape of the eye, the spherical shape of the eye, and allows light to pass to retina. After the light has passed through lens, it has to pass through all this fluid and reach to retina, which it helps in. Okay, if it is not there, eye would literally collapse like a flat balloon. It will be a flat balloon and it will be pachak. Okay, so that's what happened if vitreous humor is not there. See beta, vitreous humor is liquid, okay, and most liquid is incompressible. That means you can't compress the liquid, you can't push it back. There are gases, you can compress the gas and put it in a cylinder, and when you open the cylinder, don't open it, but when you open a balloon, okay, you let go of the air in the balloon, it goes out, right? But when you open it, when you fill a balloon inside the water, in the balloon with water, you cannot compress it, okay. That's the main reason why this shape of the eye is maintained, because the fluid can't be compressed. So until vitreous humor is there, our eye can't pachak. But if it's vitreous humor is not there, if it's empty space, that means gases are there, oxygen, nitrogen, all these stuff are there, so it can compress. Right? So that's why there is a liquid filled inside lens and retina. Our brain or human body or this universe, whoever made our human body is very, very intelligent. Okay? Then beta, if missing, eye would be collapse. This jelly-like substance makes up to about 80% of your eye's volume. Just like atom is nearly empty, right? There are electrons, protons, but all of the space is nearly empty, right? Just like that, our eye is 80% filled with this vitreous humor. I won't call it empty, but 80% of the eye shape is just a liquid. That is interesting, right? Great. So that is our vitreous humor. Moving on, beta. Next is your ciliary muscles. Now from this, lots of questions will come. Ciliary muscles do what? Ciliary muscles do this. Because of the weakening of ciliary muscles, people can't see. So this is an important topic. So pay attention. Come back from your daydreamings. Okay, come back. Now, what are these ciliary muscles? These are muscles, but the muscles that holds the lens. You see these muscles. This part is iris. But this whole part, you see this red part that is holding the lens. This is holding the lens, right? So muscles that hold the lens at its place, in its shape, that is called ciliary muscles. Now we know that muscles change, this lens change shape, it contracts, it relaxes. So when it does that, what tries to do that? So when I'm doing a push-up, okay, what is helping me to do the push-up? My muscles, right? So similarly, when lens does the push-up, it contracts, it relaxes. Which muscles help it do it? Ciliary muscles help the lens to do the push-ups. Okay, so what's the function? Help the lens thicken or flatten, or we called it as relax or not thicken. It is contract or relax. It helps the lens contract or relax, or you can say, of course, thicken and flatten for the near/far vision. We will study about it completely, how it is far, how it is near, don't worry. Okay. Now beta, if this lens is missing, I cannot adjust focus. If these muscles are missing, what will help the eye lens to contract or relax? So for near by objects, eye lens has to contract, but there are no muscles to make it contract. So the focus will not be good. We'll see blurry visions, and that is why a lot of people actually do see blurry visions, because of the weakening of ciliary muscles. Okay, so I cannot adjust focus, leads to permanent blurry vision, similar to presbyopia. We will study about. Now I have this lens right now. So right now my lens is a little bit, my eye lens is a little bit gone. Okay, but before that, when I was in first class, okay, I was this chotu Piddu, and when I was in first class, I had an eye number, I had the specs of an power of 3, literally 3. Now, so we did lots of exercise. We saw a CD of strip of white and black, and I used to just look at that CD for so long. Now, that was because my ciliary muscles were weak. I did the exercise for a week, for a month, for 2 months, I think. I used to travel every day for 30 kilometers to do that exercise. I skipped school for the whole month. So not really a lose situation. But then after that, I got healed. So when you train muscles, they get good, right? I used to drink very healthy juices, and they used to take me for exercise. Similar, the things we do in gym, we do with all our muscles. You have to practice these ciliary muscles as well. So after that, I got cured, and I didn't have this specs for a longer period of time. After that, phone came into the picture. That's a different topic. But I'm trying to say that these ciliary muscles are one of the reasons you cannot see blurry. It's not always that you need a specs. Get it checked to a good doctor, because when I got checked, they were like, just the ciliary muscles are weak, lens is perfect. So I got the specs out in like a month or 2, and then I didn't use specs for a longer period of time. Okay. So this is one of the reasons that people don't see blur. People don't see focused and good images. They see blurry images. Okay. These muscles work automatically. You see some nearby objects, they adjust themselves. You see some faraway object, they adjust themselves. Right? So you never feel them working. Of course, you won't feel them working. Now beta, next thing after ciliary muscles we are going to see is your retina. Now I'm talking again and again that image is formed. We see the object. But where do we see the object? We see the object when it is formed on the retina. When it is formed on this particular retina. Correct? Now beta, thin layer. Now what is on this retina? Very sensitive cells. Very sensitive cells are there at the back of the eye. Why all these things are written? Okay, at the back of the eye. So on the back side of the eye, your eye is completely round. So on the round side, end side, inside, you have so many light sensitive cells which are called rods and cones. So these do what? They convert, these are so many cells, okay? So they convert these light signals. Here you are getting light rays, but your brain will not understand light rays, right? So this cells beta, they convert light into electrical signals for the brain. Now, if this is missing, where the image will be formed? No image will be formed and complete blindness will be there. Okay. Now, this retina has 120 million rods and 6 million cone cells, making you a living HD camera. Okay. So, that's the main part of this retina. Done. After this retina beta, now the signal is converted, but it has to be sent to brain to analyze what we are seeing, right? So that work is done by your optic nerve. You see this part? You see this part? This beta is called your optic nerve. Done. It's a bundle of nerve fibers. So many nerves are there, nerve fibers are there. So it's a bundle of nerve fibers connecting our eye to the brain. Then it carries image signals from the retina to the brain. You have this brain here. This is your brain. So it connects the eye, the signals to the brain. It carries the signals to the brain. If it is missing, you would have healthy eyes, but you will still not be able to see the image. The image will be formed on your eye, but it will be of no use. There will be no sight. You would have healthy eyes but no sight, like a camera with no cable to display screen. So you don't have a display screen. Your brain will not see the image. It doesn't reach the brain that you're seeing the image. Okay. The image formed on the retina is actually inverted. Now this is a very interesting thing. You studied about convex lens. Now go back and remember what kind of image is formed by convex lens. Ma'am, convex lens is related to concave mirror. Concave mirror forms real and inverted. So convex lens forms real and inverted image. So am I seeing everything inverted? So you are actually like this. No, I am actually like this. What your brain is doing, your retina is getting an inverted image. But your brain is very smart. When all the signal reaches your brain, it inverts it back and shows us the real thing there. That is actually in the world. Okay, great. Then beta, talking about that, after we have power of accommodation. Good. Now we studied about that lens can shift its size. It can contract, it can relax, it can get thickened, it can get flattened. Okay, it can change its focal length. Small focal length, big focal length. Done. Now, what helps to do this? Ciliary muscles. We also studied that. So these ciliary muscles, beta, they help to do it. Now, how does they do it is the main question they have asked once in your examinations. Okay, they control the shape of the lens. Now, when these are the muscles and this is the lens, okay, this is the lens, let's say, and these are the muscles. When these muscles contract, when these muscles beta, they contract, let's study about relax first. Okay, when these muscles relax, your lens is like, I will chill now because muscles are relaxed. So lens gets this big. Okay, it फैल जाता है ऐसे. So lens gets thin. It gets big, it gets thin. Right? So our focal length, what beta? When this is your lens, okay, held by ciliary muscles, this is your lens. So when muscles relax, it goes relax. So its focal length increased. Right? So when muscles are relaxed, focal length increases. When focal length increases, we see distant objects clearly. 3 things you have to remember. When muscles relax, lens will become thin. That is understandable. I told you, right? They relax. So relax, focal length increases. Focal length increases, and when the focal length increases, we can see distant objects clearly. Okay. Similarly, for when the muscles contract, now muscles are like, I won't let you even go here from there. Okay, so they contract, it gets scared and it contracts like a little baby. Now, can you see the focal length is less? Here the focal length is more. focal length is more, here the focal length is less, right? So focal length decreases. When the muscles contract, lens becomes thick. Lens becomes thick. When lens becomes thick, focal length decreases. And when the focal length decreases, the object distance decreases. That means nearby objects are clearly. How will you remember? Focal length increases, the distance of object, use the distance of object, it also increases. That's why we can see distant objects clearly. When focal length decreases, the distance of object also decreases. We can see nearby objects very clearly. Can understand the analogy? This is how you will remember it. Done? Understand? Now, there is one more thing, something called elasticity. Have you pulled a rubber band so much that it loses its elasticity and now it's like just weak? It don't go back to its original shape or size. We all have done that somewhere. Or we wear clothes which have elastic in them. You'll see after some time, or if you let your move to friend wear it, you'll see it gets loosened up. Okay, so what is happening? They are getting so much stretched, so they get bad shape. Now elastic we can change. Can we change the length of our eye lens? No, we can't. So beta, there is a limit on how much the lens can get thick, how much the lens can get flat. If it gets too thick, now it's like, okay, don't press me more, I'll break. But you're like trying to press it, it'll break. Literally break. So that is why there is something called limit of accommodation. What is limit of accommodation? The focal length of the eye. That means now I have thin lens, I have bigger focal length, I have thick lens, I have smaller focal length. So this focal length of the eye lens cannot be decreased below a certain minimum limit. Why? Because the lens will contract a lot. And try to keep your copy here and read it for 2 minutes. You will see your eyes will start paining. Why? Because the lens is paining. There is so much strain on the lens. It cannot read this close book. There is so much strain on the lens. It starts to pain. So why it is paining? Because it can contract. For nearby objects it contract. For so much nearby it has to contract even more. And when it contracts, when you contract your muscle, it will start paining, right? It will start paining. So your ciliary muscles start to pain, the lens starts to pain, and you cannot contract the lens after a certain limit, and that limit is called limit of accommodation. Done? Now beta, the near point, that means the object, the point where you can see while without restraining, without getting pain in your lens, is the near point. That is your 25 centimeter. That is also called least distance of distinct vision. That means at that distance, that is the least distance from where you can see distinct objects, different objects clearly. Okay, so the closest distance at which objects can be seen clearly without strain. Okay, far point, how far your eyes can see. Your eyes can see at infinity technically, but of course we don't. But in general, a healthy eye should see till infinity. Okay, further distance up to which we can see clearly. Near point is the closest distance up to which we can see object distinctly. If you come closer, you will see the words are getting blurry and mixed together. Okay, that's why we keep our copies at 25 centimeter away from our eyes, because that is the least distance that where you can see the objects distinctly. Okay, hence a normal eye can see objects clearly from 25 centimeter to the infinity. So this is your eye, very sundar, and this is 25 centimeter, correct, and this is infinity. So anything near this area, from within 25 centimeter infinity, you can see clearly. But if anything comes here, it gets blurry. After infinity, there is no point. Okay, Great. Now beta, after this, okay, we have a very important question, and these kind of more questions will also come based on whatever we studied in these slides only. Nothing will come out from these slides. The power of accommodation of a lens is very important property of the eye lens, which is mainly handled by what? Power of accommodation is what? My ability of my eye lens to change its focal length. Contract, relax, thicker, flatten, thicker, flatten. So who is the fun thing that helps the lens doing this? Vitreous humor, ma'am, it gives the shape. Ciliary muscles, oh, ciliary muscles are used to contract and relax the eye lens. So that is answer. Lens itself, no, cornea has no role in the eye lens. So what is your answer? B. Ciliary muscles is your answer. Ciliary muscles is your answer. Great. Next beta, we have defects of the vision and their correction. Now this topic is beta a little science heavy, a little physics inclined. Okay, defects of vision and their correction. That means I am wearing this specs. Why am I wearing this specs? Because if I don't wear it, I'm not able to see clearly. People are wearing all different kinds of specs, not the frame I meant, the lenses I mean. Sometimes people can't see this much the object that is placed here. Sometimes they can't see far away objects. Sometimes they can't see nearby objects. Sometimes they can't even see midway objects. So what are all these defects? Why do they occur? What is their correction is what we are going to study in this particular section of this chapter, that is called defects of vision. 1 or 2 questions will definitely come from this particular section. It is the most important of this chapter. So pay attention very clearly. Okay. Now beta, 3 defects are what? First is myopia or nearsightedness. Second is hypermyopia or farsightedness. Third is presbyopia. Now let's see them one by one. Talking about myopia, nearsightedness. When we say nearsightedness, that means the near objects is clear. They are fine. I can see nearby objects clearly. But the far away objects, like I'm sitting on a bench, I'm not able to see the board clearly. I'm not able to see the face of my friend coming from afar clearly. So all those cases where I cannot see far away objects clearly, but I can see nearby objects clearly, that is called myopia or nearsightedness. Means I can see nearby objects clearly, but not the far ones. Okay. A person with myopia can see nearby objects clearly but cannot see distant objects distinctly. Distinctly means they are not different. So at so much far away, there are 2 dots. Not so big, not so small, but 2 dots. So a person who cannot see them clearly will see them merged together, right? So distinctly means different. I'll be able to see, but it will be blurry. If it's blurry, it will be mixed together, right? So they won't be distinct anymore. Done? Now, a person with this defect beta has the far point nearer than infinity. What does this mean? We just saw that the far point of a normal eye, a healthy eye, is infinity. I should see infinity objects very clearly. But I cannot. That's why I'm wearing a specs. Now, how much far can I see the objects clearly? That will be my far point, my personal far point. In normal healthy human eye, the far point is infinity. That means I should see infinity objects clearly. But for me, I cannot see infinity objects clearly. So I see 10 meters. Till 10 meters I see clearly. So 10 meter will be my far point. Understood? A person, so far point moved from infinity to closer to the eye, to 10 meter. Okay. So a person with this defect has the far point nearer than infinity. What is happening, beta? In a myopic eye, the image of a distant object is formed in front of the retina and not at the retina itself. Now, understand this very carefully. Focus on this particular section. Can I zoom it? Yeah. So focus on this particular section. What is happening, beta? See, this is your normal human eye. What happens? There is an object Okay, all the rays are coming, this is your eye lens, they refract and the image is formed on the retina. That's what we studied in the first part of this chapter. All the images formed on the retina. Now in case of myopic eye, what happens? The image, instead of being formed on the retina, it forms in front of the retina. Image is forming in front of the retina. Now you tell me, if the image is not formed clearly on the screen, will it be clear? It will be blurry, right? It will be out of focus. So that is what's happening here. All the light rays coming, they are not getting focused on the retina. They are getting focused in front of the retina, somewhere inside vitreous humor. That's not the screen, so image will be pretty blurred. Right? Now, how will you correct this? So, beta, to correct this thing, let me move it back. Okay. Now, to correct this thing, beta, we use a type of lens. That means I am wearing a specs. What is a specs? It is a lens, right? So I am correcting my vision. What is happening? In a myopic eye, the image of a distant object is formed in front of the retina. And not on the retina itself. Why this is happening? Let's understand that first. Why is this happening? Ma'am, if this is where the image is being formed. If the image is now in front of the retina, this is retina, in front of the retina, so my eyeball got bigger. That can be one case. My screen got further away, or it got, first the eye was like this, now my eyeball got bigger. So the image is focusing at the same point. The screen moved away. Right, so that's the one thing. So excessive elongation of the eyeball, we call it, with excessive curvature, no, elongation of the eyeball. Excessive curvature of the eye lens means this is the focal length of eye lens and it is focusing the image here. Now if it contracts, its focal length will decrease. Now there is the screen. This is the screen. Okay, understand from this. This is the screen and this is the eye lens. Now it focus all the things here. But if this eye lens, it contracts, it gets smaller, its focal length will move nearer and now it is contracting, it is converging all the rays here. Instead of on the retina, it is converging all the things, all the rays in front of the retina. And that is the two main causes of myopia, and this is important. They can directly ask what are the main causes of myopia. Then what is the correction? Now come to the main point. Beta, either we use concave lens of suitable power. To correct myopia, we use concave lens of suitable power. Now what does this concave lens do? Let's understand it clearly. Now look at this particular slide, at this particular diagram. So what happens? Now this is my concave lens. I can clearly see that this is my concave lens. Understood? This is my concave lens. Now what it does? See very carefully, okay? All the rays are coming, and if the concave lens is not there, they are getting converged in front of the retina. Right? So what I need to do? I need not it to converge it on the retina, not in front of, on the retina. So what it does, beta? My far point is infinity. So from infinity, all the rays are coming. And this concave lens, it does what? It makes a virtual image on the same side. So this object which is at infinity, its image is being made at this 10-meter mark. That is my far point now. So this concave lens makes the image of this object at this 10-meter point first. It's a virtual image. It does not need a screen, right? So it makes this virtual image at the 10-meter. Now, since my far point was what? 10 meter. I can see objects at 10 meter clearly. Now from this 10 meter, the rays will go directly into my eye lens. And now my eye lens can converge fine. Now my eye lens will converge the rays directly on the retina, not in front of the retina. The rays coming from infinity, it was getting converged in front of the retina. So we did what? We inserted a concave lens. This concave lens does what? It made a virtual image of the object that was at infinity, it made its virtual image at 10 meter mark, which is my far point. Now this far point, from this far point, the rays will go directly into the convex lens of my eye lens, and it will converge the rays directly on the retina. Understood? Understood clearly? Very good. Now beta, moving on, let me take this back at its original position because you will be getting PDFs. Okay. Now beta, moving on to the next thing. Will this won't work? So the next defect we have is our hypermetropia. This was myopia. Next we have hypermetropia. Now it's just the opposite of what we studied. What we studied? We studied that in myopia I cannot see far away objects clearly, but I can see nearby objects clearly. In hypermetropia, I can see nearby objects not clearly. I cannot see nearby objects, but can see far away objects. This also happens. Yes. This happens a lot. You've seen your grandparents or parents sometimes that right now they're fine. They can see everything. But when they read a book, they put their spectacles on. When they read a book, when they read a newspaper, when they use their phone, they put on the spectacles like this and they use like this. Right? I'm not mocking anyone. I'm just, it's a little cute. Okay, so they use those lenses, they use those specs to correct their vision. Right? Now beta, that is what the person with hypermetropia can see distant objects clearly, but they cannot see nearby objects distinctly. Again, distinctly means two distinct objects. Right? The near point for the person is farther from the normal near point. Now for a healthy eye, we know that near point is what? 25 centimeters. I can read this much, but a eye which has hypermetropia, the near point moves further away because they can see far objects clearly. So it moves further away. So you have also seen that they might keep their newspapers or books here, not here like we keep it, sometimes something far away from them. Right? Why? Because they can see far objects clearly but not the near objects clearly. Okay? Why is this happening? Now, in this, what is happening? In myopia, the image was forming in front of retina. Here, it is forming behind the retina. It is forming behind the retina. So this is because the light rays from a close by object are focused a point behind the retina. Done? Something like this. This object, this is the near object now. Okay. So from this rays are going and they are getting converged behind the retina. Screen is this. This is screen. This is retina. But the image is being formed behind the retina. Objects, the rays are not converging at the screen. So image will be blurry. What is the cause of this? Maybe the cause will be the focal of the eye lens is too long. Of course, the focal length is too long. So now it is, instead of focusing on the retina, it is focusing behind the retina because focal length increased. Right? Then beta, the eyeball has become too small. Here I have an eyeball and the image is formed somewhere here. So eyeball got smaller. Image is still here, but the eyeball got smaller. So the eyeball has become too small. Now, to correct this, we use convex lens. How do we do that? See, now look at this particular diagram very carefully. What do we do, beta? This is my object. Okay, this is my object. This is now my near point. Why? We said that the near point has shifted away. So any object that is at here, my near point is this, but the object is placed here. So I won't be able to see it clearly. It should be here, right? So this convex lens does what? The rays will go and this will form again an virtual image. Remember the sixth case of convex lens where it forms virtual image on the same side of lens, right? So beta, what it will do? It will form a virtual image here on the same side of lens, and now this is a virtual image of my object at my new near point. My near point shifted from 25 centimeter to 1 meter. So an object, this lens is doing what? All the rays that going from this object, it is making an image now at here. So the object is technically here, but the lens made the image here. Now from this point, the rays will go inside my eye lens, not the specs, my eye lens, and it will be focused on the retina. It makes the image further away because my near point shifted away. Now the rays will go and they will be focused on the retina. Done? Understood? Very easy, right? Let me just undo all these so that it goes to the exact position. Okay, great. So, understand why are we using convex lens? Why are we using convex lens? So, myopia, we use concave lens as the corrective lens. Hypermetropia, we use convex lens as the corrective lens. Now, you will get lots of questions on this. So, your sign conventions, your basics from the light chapter, concave lens, convex lens, its image, distance, 6 ray diagrams, 2 ray diagrams of concave lens, 6 ray diagrams of convex lens, all should be very clear, and the U, the V, smaller, greater, image, virtual, red, real and inverted, everything should be very clear, okay? But before that, there is a third, what is it called? Defect. Okay, there is a third defect, that is beta presbyopia. Now I told you, remember in the starting talking about ciliary muscles. Now as we grow old, all the muscles in our body gets weak, right? All the muscles in our body gets weak. Similarly, ciliary muscles in our body also gets weak. So, as we grow old, as the old age, the ciliary muscles starts to weaken, and these are the muscles that are holding my lens. So, they will not be able to hold the lens with full efficiency. They will not be able to contract or relax the lens fully with full efficiency, right? So, you will see that in today's area, in today's time, everybody is getting these lenses and specs. But our grandparents, they didn't have lenses and specs, right? Their vision was good because they were eating healthy, there was less pollution, there was less screen times and all that stuff. But they also have specs now because ciliary muscles are weakened. That is not because of that is not because lens has gone bad. That is because the ciliary muscles have gotten weakened. Okay, so the power of accommodation of the eye usually decreases with age. It usually decreases with age. Power of accommodation means the ability to contract or relax the lens, right? So the near point recedes away. The near point recedes away. Hypermetropia, near point is here, it goes away. So the near point is also receding away. That means difficult to see nearby objects. And the far point which was infinity, it also comes near. So the near point goes away, far point from infinity comes below. Now you can only see between 5 meter to 10 meter clearly. You can't see closer than 5 meter, you can't see farther than 10 meter, right? That is beta presbyopia. It happens due to the weakening of ciliary muscles. It happens due to the gradual weakening of ciliary muscles, and which diminishes the flexibility of eye lens. Done. How do we correct this one? Now, ma'am, how do we correct this one? We use concave lens, convex lens for every time we change our specs. When we need to see far away, we put concave lens. When we need to see nearby objects, we put convex lens. That's not the case. So, scientists have come up with a very beautiful thing, and that is bifocal lenses. What are these? Bifocal lenses. What are these? So, you see, this looks something like this. What is this? See, reading, we do it while looking downwards, right? We do the reading while looking downwards. When we look downwards, so the downward part is used to see what? Nearby objects clearly. It should see nearby objects clearly, right? And in which defect my near point recedes away? Hypermetropia. So hypermetropia, which lens is used to correct that? That nearby objects can't be seen clearly. So book is not seen clearly. The image should be made a little further. Who does that? Convex lens. So which lens is used to correct hypermetropia? Convex lens. So the lower part, this lower part of the specs, it will be made of hypermetropia or convex lens, right? The upper part, it is used to see distant objects clearly. Distant objects clearly. And in which defect we cannot see distant objects clearly? Ma'am, myopia. Which lens is used to correct that defect? That is my concave lens. Concave lens. So in one single lens, the lower part is convex lens to read. The upper part is concave lens to see further objects clearly. That's why if you have noticed, you will see the people read like this. They read like this because they are reading from the lower part of the lens. The lower part of the lens. Okay, done. Great. Now beta, moving on, and they have sometimes asked this question. Now I told you that this particular section will have all the questions, so we are moving towards our question section. So get a paper, get a notebook, pause this video, go and get the paper and notebook, write down first all the formulas, sign conventions from the light chapter, mainly of lenses you will need here. Okay, great. Now first question on your screen, everybody. What is this? The near point of a far-sighted person. Far-sighted person is what? Beta, near-sighted is near-sightedness. We call that as we called that as myopia, right? Myopia was near-sightedness. So hypermetropia will be what? Hypermetropia will be what? It will be far-sightedness. That means far away objects can be seen clearly, but nearby objects can't be seen clearly. Done? Now, the near point of a far-sighted person, that means hypermetropic eye. We call it hypermetropic eye. Okay, person is 40 centimeter. So the near point has gone from 25 centimeter to 40 centimeter. Near point is 40 centimeter. He wishes to reduce it to 25 centimeter, obviously, by using spectacles. What power and nature of the lens he should use? So ma'am, very first thing, hypermetropia, which lens we used to correct it? Beta, we used convex lens to correct hypermetropia. So this is wrong and this is wrong. It's either convex lens or convex lens. First or A option or C option, right? Now, we need to find the power. How will we find the power? We studied the power formula, 1 by focal length, right? How will we find the focal length? C. Now beta, every time, this is a very important point, note it down, write it somewhere. Write a note and write it there. Every time in a numerical, a near point or a far point is given. A near point or a far point is given. That is your V. V will be your near point or your far point. It is very important. All the numericals will be like this. So write it down. Near point or far point will be your V. V is your image distance, right? So in this, V is what? 40 centimeter. So V is 40 centimeter. Done. He wishes to reduce it to 25 centimeter. 25 centimeter. He wants his near point to be 25 centimeter. Right? So his near point is what, beta? His near point is 25 centimeter. He wants it to be reduced to 25 centimeter. Okay, wait a second. Near point of a far-sighted person is 40 centimeter. He wishes to reduce it to 25 centimeter. Great. Works. Yes, works. Done. Good. So near point is given as 40 centimeter. The near point he wants is 25 centimeter. Now understand this. What does he want? He wants that this is the image. This is the object. The object is placed at 40 centimeter. He can see it. But at 25 centimeter, he can't see it. Okay, so when you place an object at 25 centimeter, what his specs will do? His specs will make an image of this 25 centimeter at 40 centimeter, and from this 40 centimeter, the rays will go into his eye lens and perfect image will be formed. So what it did, an object is at 25 centimeter, it made an image at 40 centimeter. So this is your image distance, this is your object distance. You get the point? This is your object distance, this is the image distance. Just remember it. Anywhere in the question a near point or a far point is given other than 25 centimeter or infinity, that will be your image distance. That will be your image distance. He wishes to reduce it to 25 centimeter. That means he wants to see 25 centimeter objects clearly as well, right? So how do we do that? Now we have V and U. We have, this is your U, right? U is 25 centimeter. One more thing, everything in these numericals will be minus. U and V will be minus for these lenses, not your eye lens, these lenses. Okay, the corrective lens, what power and nature of the lens he should use. So he should use a corrective lens, right? So V and U are given. U is what? Minus 20 centimeter. V is what? Minus 40 centimeter. Minus 40 minus 25. Okay, minus 25 centimeter. And it's a what? It's a convex lens. That we already figured out. So we just have to find using lens formula. It will be 1 by V minus 1 by U. 1 by V is what? Minus 1 by 40 minus of minus 25. Done. This is 1 by V. If I take the LCM, what will be this? Okay, let's just put this as 1 minus 1 by 40 minus minus plus 1 by 25. 1 by F equals to this. Now if you take the LCM, what will be the LCM? But possibly the LCM will be 200. Let's just simply take 200. 40 into 5 will be 200. So this will be minus 5 plus 25 into 8. 25 into 8 will be 200. So this will be 8 equals to 1 by F. Right? So this will be 3 by 200 equals to 1 by F. So F will be what? 200 divided by 3. Understood? 200 divided by 3. Now, beta, power is what? Power is 1 by F. 1 by F means what? 200. F is, yeah. So 1 by F will be 3 by 200. It will be 3 by 200. But here's a catch. Here's a catch. This is centimeter. Power formula for centimeter is not 1 by F. For meter, it is 1 by F. So this will be 100 by F. When F is in centimeter, this is in centimeters, right? So this will be 2 by 3, which will be 1.5 plus diopter. So your answer will be plus 1.5 diopter convex lens. Plus 1.5 diopter convex lens. A will be your answer. Understood the whole scenario? Now let's pick up some pace. Okay, next question on your screen. How the defect of vision where a person can't see far away objects can be corrected? Now, far away objects means he has myopia. He has myopia. He cannot see far away objects clearly. To correct myopia, we use concave lens. To correct myopia, we use what? We use concave lens. By using concave lens. Done? Understood? Okay, very easy. Next. Oh, this is a good one. Study it carefully. Study the diagram below and answer the following. Name the defect of vision depicted in the diagram. What is the first thing you see? Ma'am, the image is not formed on the retina. It is formed behind the retina. First thing you see that the image is formed behind the retina. Done? That's the first thing you will see. Ma'am, in which case image is formed behind the retina? Myopia or hypermetropia? Myopia, it was in front of the retina. Myopia, it was in front of the retina. So, in here it will be what? Behind the retina. That means it is beta hypermetropia. Hypermetropia. You understand how will we go through these questions? This is hypermetropia. List 2 causes of the above defect. Ma'am, the eyeball is small. Maybe the eyeball has gotten small, right? Or the focal length of my eye lens, it increased. That's the 2 causes of hypermetropia. The focal length increased, so it is focusing behind. Eyeball got shortened. Image is being formed at the same point, but the eyeball got shortened. Right? Draw a ray diagram for the correction of the above defect using an appropriate lens. Which lens is used for hypermetropia correction? Ma'am, for hypermetropia, which lens is used? Correct? Not correct. Let me know in the comment section with the timestamp. Okay? So for hypermetropia, ma'am, we use convex lens. We use convex lens. So this is your eye. Okay? Somewhere like this. Okay? So beta, this is your eye lens. Now I have to correct my vision. So I will use a convex lens. This lens will do what? This is my object. So what will happen? The rays will go and it will form a image behind the actual object near my new far point, near my new near point. My near point has shifted because of hypermetropia. So the near point has shifted. This is the new near point. At the new near point, our virtual image will be formed, and from this virtual image, the rays will go inside my eye lens and the image will be formed on the retina. Now, you don't have to do this much. Just do this. Oh, sorry. Just do this one. Okay, now the vision has been corrected. Done. Great. Moving on, we have next question, that is an assertion reason question. A person with hypermetropia cannot see nearby objects clearly. That is true. The eyeball is too long and the focal length of the eye lens is too short. Let me make sense. So hypermetropia, that means the image is formed behind the retina. Image is forming behind the retina. Okay, behind the retina, that means eyeball gets shortened or focal length increases. Focal length is too short. Eyeball is too long. It's opposite, right? So assertion is true, but reason is also true, but they are not the correct explanations of each other. Both A and R are true, but R is not the correct explanation of each of A. So B will be your final answer. Done? Next beta, the twinkling of stars in the night sky. Okay, this is a question after that. We'll do. The image distance from the eye lens in a normal eye, when we increase the distance object from the eye. What they're trying to say? They are saying that this is your eye. Okay, this is your eye and this is the retina. Now, the image will always be formed on the retina, right? Tell me this point. The image will always be formed on the retina, no matter if the object is here or here or here or here. So they're asking the image distance from the eye lens. The image distance from the eye lens in a normal eye, when we increase the object distance from the eye, will it change? No, it will not change, right? It will remain unchanged. Then it is always going to form on the retina, not behind or front of the retina because of changing object distance. No, it will form in front or behind because of some defect, not the position of object. Done? Great. Next question on your screen, beta. After tracing the path of ray of light, through a glass prism for 4 different values of angle I. This is a light chapter question. I don't know how it came here. Okay. Every ray diagram was analyzed and the following conclusions were made. This is some... Okay, it's a prism. Okay. Again, questions after the prism. We'll study prism as well. Don't worry. Then we have... question. We'll do. Yes. A person with a myopic eye. Now, first thing, when you read about myopia, hypermetropia, whatever, the first word you see, you have to write it down. What is this, ma'am? Myopia. Myopia means that first thing, they cannot see far objects clearly, but they can see nearby objects. They cannot see far away objects. Now, the lens we use to correct this is concave. That's what you have to write. Concave lens. What is the value of focal length of, what is the sign of focal length of concave lens? Ma'am, it is negative. We studied in the light chapter. Whenever you see a word myopia or hypermetropia, you have to do this first step first. Okay? Now, a person with myopia cannot see objects beyond 1.2 meter. That means what? The far point came nearer to the eye. 1.2 meter is the point till where they can see clearly. After that, it's blurry. right? So far point shifted from infinity to 1.2, right? So this is what? This is your far point. This is your far point, that is 1.2 meters. And I told you far point or near point given will be what? Your image distance. You have to write it down. Image distance minus 1.2 meters. Every time the image distance will be minus 1.2 meters. Remember that. Next, what should be the type of corrective lens used to restore the proper vision? We didn't have to do all this calculation. Just myopia, we already wrote it. We need to use the concave lens to correct the vision. See, we didn't even read the question. We already have the answer if you follow my strategy. Okay? Great. Next question. The near point of the eye of a person is 50 centimeter. Again, what is given? Near point is given. Near point is what? Near point is your image distance. Image distance is always what? 50 centimeter minus. Done? Minus. We already know a lot of things. It's easier to write them down than to be confused later. Okay? Find the nature and power of the sorry. Corrective lens required by the person to enable him to see clearly the objects placed at 25 centimeter. They are saying that the objects placed at 25 centimeter. So minus 25 centimeter is our object distance. From the eye, we have to find the nature and power. How will we find the power? By finding the focal length. How will we find the focal length? By using lens formula. Let's do it. Okay, our solution. What is the solution? Ma'am, by using lens formula, we have 1 by f equals to 1 by v minus 1 by u. 1 by f I have to find. 1 by v is what? Minus 1 by minus 50. Why did I write 5? Yes, 1 by minus 50 minus of minus 25. Done. Just take the LCM. The LCM will be simply 50. This will be minus 1 minus minus plus 2. 25 2s are 50. 1 by f. So 1 by f comes out to be what? Minus 1 plus 2. 1 by 50. So focal length is simply 50 centimeter. 50 centimeter. Now, this is done. You tell me one thing. The near point of a person is 50 centimeter. That means near point has shifted from 25 centimeter to 50 centimeter. That means it is what? It is hypermetropia. That means it cannot see nearby objects clearly. That's why the near point shifted from minus 25 centimeter to 50 centimeter. Right? So it is hypermetropia. Hypermetropia, which lens is used to correct hypermetropia? Ma'am, convex lens is used to correct hypermetropia. What is the sign of the focal length of convex lens? Positive. Because of the x, rotate the x, positive. Convex lens, positive focal length. Positive focal length, we got. And hence our answer. Find the nature and power of the connective lens. The power, we still have to find. Okay. Power, beta is 100 divided by focal length when focal length is in centimeters. So 100 divided by 50, that is 2. So power is plus 2 diopter and the lens used is what? Convex lens. That means it is a hypermetropia. Understood? Good. Okay, give me a thumbs up if you have understood this question. It's a really important question, and if you have understood it, then clapping for all of you. Okay, great. Next question on your screen. A student needs a spectacle of power minus 0.5 diopter. So what is given? Power is already given in the question. So power beta is minus 0.5 diopter. For the correction of his vision. Done. Name the defect of vision the student is suffering from. Just from the power we have to find out. Now look at this. How crazy is this? How easy is this? And how funny this is. See, power is minus 0.5 diopter. So just do not have to find the focal length. We don't have to do nothing at this point. Just see what is the sign. Ma'am, the sign is negative. Negative. Now power is simply 1 by f. So if power is negative, the focal length will also be negative, right? This is also the sign of focal length. So focal length is also negative. Which lens has negative focal length? Concave lens or convex lens? Ma'am, concave lens have negative focal length. Concave lens has focal length negative, right? That is your answer. Name the defect of the vision of the student suffering from concave lens. Concave lens is used to correct which defect? Ma'am, it is used to correct myopia. It is used to correct myopia. Understood? Great. Find the nature and focal length of the corrective lens. Nature is already here, concave lens. So, answer number 2 is already done. First answer, second answer. What is the focal length? That we have to find. Simply do this 1 by f. So, power is minus 0.5 diopter. Power is 1 by f. So, okay, power is 1 by f. So, this is what? Minus 0.5 diopter equals to 1 by f. So, if you just cross multiply, f will come here. This will be minus 1 by 0.5. F will come here, 0.5 will go here, right? So, this goes here. So, this will be 10 by 5. So, minus 2 meters. Make sure you don't write centimeter because this is diopter. 1 by f is meters. So, this is the third. Oh, this is also the second answer. So, focal length is minus 2 meters. Concave lens has negative focal length. Focal length is negative. See. Okay. List 2 causes of this defect that you have to list in the comment section. List 2 causes of this defect. What defect? Myopia. What is this? In front of the retina image is formed. So, elongation of the eyeball or excessive curvature of the focal, excessive curvature of the eye lens or decrease in the focal length of the lens. Done? Great. Next question, beta. A person wears spectacles of power minus 2.5 diopter. Again, what is given? The power is directly given to us. Power is minus 2.5 diopter. Name the defect of vision he is suffering from. Again, the same thing you have to follow and tell me which defect is this. Now, what will be the focal length of the corrective lens? So, focal length is simply 1 by f. Minus 2.5 equals to 1 by f. F will be minus 1 by 2.5. So, this will be 10 by 25. Right? So, this is simply beta 0.4. So, minus 0.4 meters will be your final answer. That is your focal length. Tell me in the comment section, which lens it used to correct its, correct its vision. Which defect is it? It is, and which lens did he use to correct its vision. Great. Now, moving on to the next question. Yes. A student needs a spectacle of minus 0.5 diopter for the correction of his lens. Name, this is the same question. Okay. Simply, power is negative. Power is negative. Focal length is also negative. Focal length is negative of which lens? Ma'am, concave lens. Concave lens is used to correct which defect? Ma'am, myopia. For myopia, power will be negative. Done? Myopia. Great. Next question. The near point of a hypermetropic eye is 1 meter. See, 2-3 things are given here. Let's write it down. First, hypermetropia. Hypermetropia is corrected by which lens? Convex lens. Convex lens has focal length what? Positive. These are the information we know. We written it down. Done? Near point is 1 meter. So, what did I tell you? Near point will always be image distance. Always be negative. So, minus 1 meter. Done? What is the power of the lens required to correct this defect? We have to find the power. Assume that the near point of the normal eye is 25 centimeters. See, even if this is given or not, in some questions it won't be given the near point of normal human eye. So, you will just assume that it is 25 centimeter. Okay. So, U is given as 25 centimeters. Minus 25 centimeter. Correct. Good. So, this is you have to find. ठीक है. Then solution. Now see बच्चा, what we have to do? Correct. So, okay, using length formula, 1 by f equals to 1 by v minus 1 by u. Why we used length formula? Because power is 1 by f. How will we find f? By using length formula. Okay. Just fill all these values. 1 by f equals to 1 by v. V is minus 1 minus of minus 25. Done? Is there any problem here? Something is wrong here. What is wrong? Ma'am, units. This is meter, this is centimeter. Both should be in centimeters or in meters. So, this will be what? Minus 100 centimeters. So, change it here. You have to remember all these things, okay? Minus 100 minus of minus 25. Understood? That is the thing. Now, do the calculation. What is the calculation? 1 by f equals to minus 1 by 100 minus minus plus 1 by 25. So, 100 will simply be the LCM. 100 be the LCM. This will be minus 1 plus 25. 4 is 100. This will be 3 by 100 is your 1 by f. Now, beta, you don't have to change it. Simply, power is what? 1 by f. 1 by f is what? 3 by 100. Is it true? Again, one more thing that you left. Focal length is in centimeters. So, power will be 100 by f, not 1 by f. So, this will be 300 and power will be 3 diopter. Your final answer. Done? Power will be 3 diopter. Focal length is positive. Convex length focal length is positive. Okay, great. Next question. The focal length of a lens is 10 centimeter. The focal length of a lens beta is 10 centimeter. Focal length is 10 centimeter. Now this is positive given. Okay. Let's see. Let's read it. If something else is given, write the nature of the lens. Focal length positive. That means convex lens. Done. First part. And find its power. Of course, we have to find the power. Done. If an object is placed at a distance of 20 centimeter, object is placed at 20 centimeter, object is always negative, right? From the optical center of this lens, according to the new Cartesian convention, what will be the sign of magnification in this case? Okay, this is simply more of a light chapter question. Okay, so will you do that? Will you do that? I'll give this homework. You will do that. Okay, solution as homework. What you have to do? You have focal length, you have u, right? You will be finding power simply 100 by focal length because focal length is in centimeters. Done. Magnification by using lens formula. Can you find v? Can you find v by using lens formula? So, by v, you will have magnification for lenses. It is plus v by u. So, u you have, f you have, find v and let me know answer in the comment sections. Done? Great. Moving on to the, okay, lots of questions we did and questions are finally over. A very interesting fact. Do you know that your eyes live a little longer, that a person eyes live a little longer than that person does? So our eyes keep on breathing because they take oxygen from the air. Remember? So not the exact reason, but sometimes that reason can be used. Now, our eyes can live even after our death by donating. That's why they quickly come and they donate the eyes. They donate the eyes after we die. We can light the life of a person who cannot see. Right? Interesting fact? Good. Next beta. Moving on to the second section of this whole chapter, second part of this whole chapter. I told you in the outline, right? So beta, this is refraction of light through a prism. We studied refraction of light through a glass slab in the light chapter, remember? Similarly, just using the same concept we have to study here. Now, look at this thing very carefully. Okay. And the color, this one. Now, a light is coming. This is your prism and a light ray is coming. Okay. What we will do? At the point of incidence, we will draw a normal. At the point of incidence, we will draw a normal. Then what happened? Then ma'am, after it it changes its medium. This is medium 1, that is air. This is glass. This is again air. So it is going from rarer to denser. It will bend towards the normal, right? So instead of going straight, it bends towards the normal. It bends towards the normal. The green line is the actual path of the light ray. Okay, it bends. Okay, let me just take this. It bends towards the normal, and this is the actual path. Done. Again, now at this point of incidence, I will again make a normal. Now the ray is going from, this is glass now. Okay, now the ray is going from denser to rarer. So it will bend away from the normal. So instead of going straight like this, it bends away from the normal. This is the normal. It will bend away from the normal. Understood? Very simple. Understood? A ray come, incident ray, and incident ray came. Instead of going straight, it is going from rarer to denser, so it will bend towards the normal. So this is the normal. Going here, it bent towards the normal. This is the normal. It is going from denser to rarer, away from the normal. Very easy. Okay? This is your incident ray, your refracted ray, and your emergent ray, just like in glass lab. This is your angle of incidence. This beta with normal is your angle of refraction. This is your with normal angle of emergence. Just remove this, we don't need it. Done. Now beta, there is one more thing you have to understand. If you expand this particular ray beyond this emergent ray behind, then now this is where the incident ray should have gone if there is no medium change, and so it looks like it's going there. The emergent ray, if you expand it behind, it looks like it is coming from that side, right? So the angle between this emergent ray and incident ray, this beta is called delta. Angle of deviation. So this is the incident ray, this is the emergent ray. How much this incident ray got deviated? Angle of deviation. Understand? So we have angle of incidence, angle of prism. This angle, the angle of prism is called A, angle of prism, angle of refraction, angle of emergence, and this D, angle D is your angle of deviation. Done. You can write it as D. In higher classes we write it as delta. You can write it D as well. You can write it D or delta, whatever you like. Okay, that's the whole thing about refraction of light through a prism. Done. Now beta, moving on this we have some very specific thing to learn, is dispersion of white light by a glass prism. Now you know how refraction happened, but there is a thing called white light. Now we all know white light is made up of Vibgyor, right? White light is made up of 7 different colors. And when this white light beta hits a prism that has a different refractive index. Now all these 7 colors inside the white light, they have different wavelengths, they have different speeds. So when they hit the refraction, what was the formula of refraction in light class? N1 by N2 equals to V2 by V1. That means, see, N1 is air, okay, N2 is glass. Done. N2 is glass in this case. Now this will be V2 of this light inside glass, okay, inside glass, and V1 will be air. But this is also related to the wavelength, which you will study in some time you will study this V2. See, the formula is nu equals to C by lambda. Yes, so this is frequency, this is wavelength, and this is the speed. This is speed, and this is what? V is also speed, right? So this speed is related to this wavelength, and every of these colors have different wavelength. So if we have different wavelength, we have different speed, we will have different speed. So when this white light goes into this prism, all the 7 components, they get separated because of their different wavelengths as the medium changes from air to glass. Understood? Again, as the medium changes from air to glass, the 7 components of white light disperses into 7 different colors. That is your VIBGYOR, and it is written from down to upward. VIBGYOR. Done? Understood? Very good. Now, next beta, this thing, but with a slightly different viewpoint. Now, we talked about how these scientists think, right? We talk about all these time. Now, how this thing is, Isaac Newton came and is like, okay, let me do one thing. This is a prism, whatever. This is a prism. What will happen? And it is splitting the white light into its 7 consecutive colors. What will happen if I place a prism, inverted prism, in front of those 7 colors? What will happen if I place an inverted prism in front of these 7 colors? So what happens? White light goes, it's split into 7 colors. And he placed an inverted prism in front of those 7 colors. And he saw all those 7 colors went to the prism and came out was white light. So they merged together as well when an inverted prism is placed in front of those 7 different colors. How crazy is that? Okay. Different colors of light bend through different angles. Okay, it is bending here, it is bending here. Violet color bends the most, and blue the least, then yellow, orange, red the least. Okay, blue, violet the most, red, yellow the least. Okay, different angles with respect to incident ray as they pass through a prism. The red light bends the least, while the violet light bends the most. Rays of each color emerge along different paths and thus become distinct. So the violet is bent the most, red is still here. So we can see red and violet differently. Okay, great. Next beta we have on this is a very important topic, formation of a rainbow. Now in rainbow we also see VIBGYOR, right? So what is happening inside a rainbow? Okay, see very carefully. Now this is your, what is this? Beta, this is your water droplet. Okay, when is rainbow formed? Ma'am, right after the rain. Right? So when right after rain, there are so many water droplets inside our atmosphere. Okay. Now inside our atmosphere, the white light from the sun, this is sun. Okay. Okay. Sun is smaller than earth. This is sun. Okay. Sun, this is my sun. Now sunlight is coming from the sun. Okay, sunlight is coming from this sun and it bounces, it hits this water bubble. Okay, now what happens? Now this is what? Air. Inside is what? Water. So medium is changing. Medium is changing, right? So beta, yes, this is air, this is water. So what will happen? I will make a normal at this particular point. Okay, I will make a normal. Let me do one thing. Let me not make it like this, and let me make it something like this. Okay, it will be easier to understand. That's it. Now I will make a normal at this particular point. Normal will be something like this. Normal will be something like this, right? So this is an incident ray, the sunlight. It is going inside the water bubble, the water droplet. Now it is normal. Now you tell me, air to water, the light will bend away from the normal or towards the normal? It will bend, ma'am, it will bend towards the normal. It will bend towards the normal. But there is one catch in it. Now the colors will split. It will act like a prism in the air. It will act like a prism in the air, and instead of just getting refracted, the light will refract like this. How will it does? Wait a second, let me just this is fine. This is okay. So something like this will happen. So what happened? This white light got split into its 7 consecutive colors. Here we have red, then at the least beta we have violet. Okay, this is violet, and inside this we have all the colors. Vibgyor. So it starts with violet, goes with indigo blue, green, let me just draw green as well, and yellow, orange, red. So this is what happens. Now at this time, at this screen, what happens? There is something called total internal reflection. What is it? Total internal reflection. Why this happens, beta? Total internal reflection. So whenever this ray is hitting on this water bubble and it is getting refracted because it has some incidence angle. Now, when there is something called critical angle, that means whenever this incident angle is greater than a particular value of angle, let's say 70 degrees. For now, let's say 70 degrees, for example. So when incident angle becomes 71 degree, then instead of going out, technically it is water, it is air. So all these just go out. All these should just go out, right? But this incident angle is now very much big. Okay, very much big, and it's bigger than the incident angle, critical angle. At this point, the incident angle is greater than critical angle, and when incident angle is greater than critical angle, instead of going out, refraction, total internal reflection happens. Means it gets totally reflected inside the water bubble. It is not a mirror, it is a bubble. It should go out, the rays should go out, but they don't, because incident angle is greater than the critical angle. So these rays will reflect like this. These rays will reflect like this, and they will come out of the water bubble. From here, now they will again refract. They should go like this, but they are refracting. So they come out like this. They come out like this. And this is your, again, Vibgyor. Understood the whole phenomena of rainbow formation? Sunlight comes, it refracts, total internal reflection happens, and again refracts. Done? And that is what we wrote here. What happens? First light refracts, then it disperses into its 7 colors, then it total internal reflection happens, then again refracts again while at the exit. Okay, the rainbow appears opposite to the sun in the sky. That is true. You can also see a rainbow near a waterfall or fountain when sunlight is behind you, because we just need water droplets and sun behind you, right? That's the only condition for a rainbow. So near waterfalls also there will be lots of droplets, right? So those droplets will act like tiny prisms in the air, and they will refract, disperse, total internally reflect, and again refract the sunlight. Done? Understood? Great. Now beta, next we are going to talk about another phenomena, that is atmospheric refraction. You go and in extreme heat, just stand somewhere which is like an empty lot, extreme heat I'm talking about, and you will see from a different, the things will see happening like this. All the layers will do like this. Okay, empty space, but you will see the things, they're bouncing back, bouncing in each other. Or when you have lit a fire, okay, you have done a bonfire, a campfire, or we celebrate Lohri in Punjab, right? So you will see that behind this, a person standing on the other side of the fire, you will see they are like dancing like this. They are not, but their image is dancing like this. Why? That is atmospheric refraction. What is happening, beta? There is a person standing here. Okay, there is a person standing here. Now, here the air is cold. Here the air is extremely hot, right? And here where I am standing, the air is again cold. Okay, now there are heat, so many particles, cold, some other particles different. So the density of particle is different. So the medium is different. Here the medium 1 is there, medium 1, medium 2, and again medium 1. Right? So what is happening? The light is coming from medium 1 to medium 2. It will refract. So let's say it is coming like this and it refracts. It refracts like this and then out again it refracts like this. So I will see that this person is somewhere here also. That's a different thing. But then the next light comes. Now it comes from here and it goes here and I see person here. Right? So the light is continuously shifting its position and that's why the person is looking like this. It's looking like this. Okay, so beta hot air is less dense. That means particles are away from each other. Hot air is less dense. Has a lower refractive index. It has a lower refractive index. Constant temperature and than the cooler air above it. Okay, constant temperature changes cause continuous bending of light. As the temperature is constantly changing, a continuous refraction, bending of light is happening. Continuously light is bending. Continuously light is bending. Okay, so apparent position of object keeps on shifting. First I think the person is here, then I think the person is here. So it keeps on changing its position, right? That's why it looks like he is dancing. Its apparent position keeps on shifting. This wavering is local effect of atmospheric refraction. Local effect means it is just in around that fire, not somewhere other, just around that fire. Localized effect. Okay, the twinkling of stars is the same phenomena on a much larger scale. Again, the stars are twinkling. Why? Because there are lots of layers inside our atmosphere, right? Vacuum, then troposphere, stratosphere, magnetosphere, ionosphere. So from all that, the ions are different, their mediums are different. So light is continuously bending until it reaches us. We see this here, this here, this here. So they are continuously twinkling. Okay. Great. Moving on, the next on this basis, beta. Oh, the same question. Why stars twinkle but planets do not? Beta, planets are very near to us. This is our Earth. This is planet. Okay, planet P. Now, all the rays that are coming, they just cancel each other's effect. They also come from all the layers, but they cancel each other's effect because planets are higher. They are this big. The stars, on the other hand, are very small. One ray of light comes and it keeps on doing this, and it goes into our eye. Even though these are doing also this, these are also doing this, but lots of rays are coming. So they cancel the effect of atmospheric refraction, the nearby objects. Done? Note, the sun is visible to us about 2 minutes before the actual sunrise, about 2 minutes after the sunset because of atmospheric refraction. Now, what happens? Again, this is your Earth. Okay, this is the Earth. So, sun will be there. The sun is setting. Okay, now we see small sun. Okay, so this is you and me. Okay, now the sun is setting, but now sun is here. Okay, sun is here. So there are lots of, again, layers in the atmosphere: stratosphere, stratosphere, magnetosphere, and all that. Magnetosphere is actually the upper one. So the light is coming and it is bending, something like this. Light is coming, bending, and if I am seeing this last ray, I am seeing this last ray coming from sun, and if I trace it back, I will see the sun is still here. Actually, the sun is still here. But the rays coming are refracting. So if I trace it back, I look like the sun is here. So sun has already set 2 minutes, but I can still see sun even when it has set. And similar the case goes for sunrise. It already came up, but it has not come up yet, but the light is refracting. I can see the sun yet, but it is not there yet. I can see in the future. Okay, great. Next beta is your scattering of light. Scattering of light is simply the deviation of light from its straight path. Beta, light travels straight, but you get some objects. There are so many objects on this earth, right? We are objects, other objects for light. So light is going and it hits this object, hits this obstacle. So it changes its path, like hut, it goes away. So it changes its path with the deflection from an object. So scattering of is the deviation of light, from its straight path when it strikes tiny particles like dust, gas, or water droplets inside the atmosphere, right? So beta, now that is it about the scattering. This is the light going, it there's a particle, it deviates, particle, it deviates, particle, it deviates. It just keeps on doing it. Okay. After that, we have Tyndall effect. Now, beta, Tyndall effect we studied in 9th chemistry as well. Okay. What is it? There are a small opening, a small opening on your on the top of your room. So light comes in, and there are dust particles, small particles. Through those particles, the path of the light is visible, and that is what Tyndall effect is. So the earth is a heterogeneous mixture. We studied about mixtures, right? Heterogeneous mixtures, that means lots of things are there. With what are there? Smoke, water droplets, suspended particles of dust, molecules of air. So when a beam of light strikes all these particles, the path of the beam becomes visible, and that visible path is called Tyndall effect. The phenomena of scattering of light, touching all these particles, the light is getting deviated from one water droplet to another gas molecule, right? So, because of the scattering of light through all these particles by the colloidal particles gives rise to Tyndall effect. Very fine particles scatter mainly blue light because the wavelength of the light is smaller and the size of the particle is also smaller. So when the wavelength of light is comparable to the size of the particle, it scatters that light. Now red light has more wavelength, so it does not scatter red color. The particles, the sky, only scatter blue colors. That's why the sky looks blue. That's the reason. So the fine particles scatter mainly blue light because of the shorter wavelength, while particles of larger size scatter longer wavelengths like the red light. Okay, and that is how we get a question, why is the color of the sky blue? Because the particles in the sky, the size of those particles are comparable to the wavelength of blue light. The size of the particles in the sky are comparable to the wavelength of the blue light, and hence it scatters the blue light. When it scatters the blue light, the whole sky looks blue. Right? Now, then why does danger signals lights are red? See, we need to see danger from a far point, right? From a far point, we need to see the danger, right? So that we can set back, right? Now, but a blue light is scattered in the sky. Blue light is scattered. So what is not scattered? Red light remains same. Out of that VIBGYOR, blue part is the whole, indigo, violet, blue, all these is scattered. So what is left? Red, green, yellow, the mixture of that is left. So it is not getting scattered. So it will travel a longer distance. It will travel a longer distance, and hence it will not scatter down. It will remain sharp and it will travel longer distance, and hence we will see danger, the red light of danger from afar. And that is why the danger signals are red. And that is where we complete our chapter Human Eye. And that is it for this chapter. We studied all the theory, we studied all the questions, the MCQs, the those questions, lots of numericals and lots of fun stuff as well. Remember to revise the defects. That is a very important topic. Okay, that is it for this video, beta. You will get the PDF in the description, and you can join this WhatsApp channel as well. Link will be in the description. The courses, we have launched 2 courses, that is for class 9th and class 10th on our AIO page. Let me just show you quickly. Where is the page? Let me show you. Yes. So beta, these are the 2 courses we have launched for class 9th and class 10th. Just click the link in the description. It is completely free. It is completely free. You will get weekly tests, weekly assignments, 40 tests. See, the one who will do tests will get good marks in boards. So it is for class 10th as well as for class 9th. Everything will be available on this channel. Unlimited access to post class replays will be there. The classes we will be taking all will be there. All the assignments will be there. All the tests will be there. So quickly go and buy now. How much the course is? 0. Both for class 9th and class 10th, the course is of 0 rupees. Okay, so there is no harm. Go join the course, and that is it for this video. I'll meet you in the next one. Tata, bye bye.